Okay, systems of differential equations. So the basic idea for a solving system of equations, we're going to need that solutions form a subspace, eigenvalues and eigenvectors create solutions, and then we'll look at the cases. So any kind of a system, right? dx dt equals ax plus by, dy dt equals cx plus dy, a, b, c, d are all constants. We can rewrite this as y prime of t equals m times y of t. Y of t is our solution curve that we want. This is its derivative. That's this part. And then m is the coefficient matrix. So a couple of things that we need to know. One is that the solutions form a subspace of the set of all functions. So what do you need to check for a subspace? You need to check that 0 is in the subspace, closed under addition, and 3 closed under scalar multiplication. And that means we can just add solutions together, multiply them, and be guaranteed that we still have a solution. Multiplication. So check 1. How do you check that a function is a solution, right? And this should be y equals 0. How do you check that something is a solution to an equation? You plug in y equals 0. So the left-hand side, the derivative of 0 equals 0. My left-hand side there. My right-hand side is that. Right-hand side, m times 0 equals 0. So left-hand side equals right-hand side. 0 is the solution to this equation. Okay, 2. Let y1, y2 be solutions. Is y1 plus y2 a solution? So can I add two solutions together and get another solution? Well, how do you check? We want to check if this is a solution, so we plug it into the equation. Left-hand side means take the derivative of our proposed solution, y1 plus y2. What do we get? We get derivative of y1, derivative plus derivative of y2. What do we get when we plug it into the right-hand side? Right-hand side, you get m times y1 plus y2. And if you distribute the matrix multiplication, you get this. But y1 is a solution. What does that mean? That means that y1 prime equals m y1. Since it is a solution, if you plug it into the equation on both sides, you get a true statement. y2 is a solution. That tells me that y2 prime equals m times y2. So these two things are equal, and those two things are equal. So if I add two solutions together, I get another solution. And then 3, let y1 be a solution. K is scalar. Is ky1 a solution? And remember that y1 being a solution means that this is true. So left-hand side equals derivative of ky1, because we're trying to show that ky1 is a solution. And that equals ky1 prime. But that equals k times m times y1, because y1 prime is equal to my1. And then we can take the k inside of the matrix multiplication, and so left-hand side equals right-hand side. So if we multiply a solution by a constant, it's still a solution. If we add two solutions together, we get a solution. So if we can find functions that span the solution space, then we can write every solution as a linear combination of these functions, right? So the solution space is a subspace. That means it's a span. So if we can find spanning functions, every solution is just a linear combination, k1, y1 plus k2, y2 of these functions. And we can get these functions through eigenvalues and eigenvectors. So why do eigenvalues and eigenvectors create solutions? So suppose lambda and v as an eigenvalue, eigenvector pair for m, then y2 e to the lambda tv is a solution to this. So being an eigenvalue eigenvector pair means you have the following property. M times v, put a little arrow v, equals lambda times v. So this is a property that being eigenvalue eigenvector pair means. So what we want to know is y of t a solution to this equation? So e to the lambda tv, a solution to y prime equals my. How do you check that? Plug it in and see if it works. So left-hand side, dy dt equals the derivative of e to the lambda t times v. V is a vector. It doesn't have any t in it. It's essentially a constant. So the derivative is just going to be the derivative of e to the lambda t times whatever v is. And the derivative of e to the lambda t is lambda e to the lambda t, and then times v. What's the right-hand side? The right-hand side is m times y, which equals m times e to the lambda t times v. But e to the lambda t is a constant. It's just a number. It can vary with what t is, but it still represents just a number. So I can take that out of the matrix multiplication. And now m times v is equal to lambda v. So we get e to the lambda t lambda v. Great. So that tells us that if I take e to the lambda t times a vector, times an eigenvector, then that's the solution to our program, to our equation. So from this theorem, we can find functions that span the solution space. If you have a matrix, a system that can be represented in matrix, find the eigenvalues and the eigenvectors, and those will give you solutions. So there'll be three cases, and these are similar from second order equations and Laplace transforms, and now this. So we can have two real distinct eigenvalues, lambda 1 not equal to lambda 2, and then the two solutions you get, e to the lambda 1 t v1 and e to the lambda 2 v2 span the solution space. Complex eigenvalues, you end up with complex numbers, but you can still build two real functions like we did with the second order equations to span the solution space. And then one real repeated eigenvalue. And there's only one eigenvalue eigenvector solution there, but you can construct another vector from the initial conditions to find the second solution. And those two solutions will span the space. So that's the plan then for the next three lectures is two real distinct eigenvalues, two complex eigenvalues, one real repeated eigenvalue.